Assalamu alaikum wa rahmatullahi wa barakatuh. Is my voice clear for everyone? And are you able to see the screen as well?
Yes, Mr.
Okay. So we are going to start directly our class since we don't have a lot of time. Okay. In the last couple of classes, we have taken design of isolated foundation. We have learned the meaning of one-way shear, two-way shear. We have learned when to calculate for the bending moment values. Now, or today, we are going to take the combined foundation. And the main difference when it comes to combined foundation and isolated foundation is how would you calculate the bending moment and how would you calculate the dimensions. Okay. Now in isolated, we have one column only. So normally we are going to place that particular column at the center of the foundation. Now when it comes to a combined footing or a combined foundation, we have two columns and we need to be careful on where to put our foundation, or where to keep the center of the foundation to avoid any moment. Okay, to avoid any moment in the sense that we don't want any extra bending stresses. If you remember, we have said there are two types of stresses. If your column is at the center, if it's concentric, then you are having normal stresses, which is P over A only. If you are having eccentric, where the column is not acting at the center, it will not only cause you to compress, it will cause you as well to bend. If you remember in eccentric, when we have drawn the diagrams. Okay, so you will be having P over A plus M over Z. Okay. Now the same thing that we are going to do in terms of a combined foundation. We need to locate the center of gravity for the combined foundation, and accordingly we are going to design, or at least we are going to calculate for the bending moments. Now if you got your bending moments, then the other steps are going to be easy for you, where you are going to get the values of K, get the values of Z, and then AS. So the same process, whatever you have done in isolated foundation, is going to be followed in combined foundation. The main difference is in how would you calculate the bending moments, and we are going to see this today, inshallah. Okay, so I have brought for you one question in which we are going to try to solve. Now this question says for you, let's see it in the whiteboard directly. This question says for you, are you able to see the screen? Is it clear for everyone?
Yes, Mr.
Yes.
Okay. So now here we have a question says that we need to design a combined footing that supports two columns. We have C1, which is 300 mm square column, and then we have C2, which is 400 mm square column as well. Okay, with dead and imposed loads. Okay, with dead and imposed loads of or as 1000 kilonewton and 200 for C1 and 1400 and 300 for C2 respectively. So now once again what the question says for us, we have two columns. Okay, this is 300. And then we have another column, which is 400. Okay. And just 1 second. There's one information which is missing. The distance, which is not given here. I can just add it in the PowerPoint. This distance. Okay. So we have been given that the distance between the two columns is 3 meters center to center. Okay. So we return back here. The distance from the center of the first column to the second column is 3 meters. Now, if the question says for us that check whether isolated or a combined foundation is to be used, you are going to do like whatever we have done. We will check for column number 1, we will check for column number 2, isolated foundations. If they overlap, we'll go for a combined foundation. But in this sense, in this particular scenario, it has been specified directly from the beginning that this is going to be a combined foundation, right? Okay, it has been specified in the question that this is a combined foundation. Now the first thing that we need to do, the first step, is to calculate the area. Let us calculate the area required for this particular foundation. Now we know that our area okay, we know that the equation of area is based on stress is equal to force over area, okay, which is rewritten as area required is equal to force divided by your safe bearing capacity, which is the maximum stress can be taken by the soil. Now we said when it comes to area, we are going to use surface loading, and then we have our SPC. Now how many loadings are there? How many loadings are there? There are 4 loadings, 2 in the first column, 2 in the second column. So we have 300, and we have 1000. So 1000 kilonewton, and then you have 200 plus 200. Okay, and then you have 1400, and then you have 300. And if you remember, we used to take 1.1, which represents the self weight of the foundation. But in this scenario, the self weight of the foundation has been given for you already, which is 250. So rather than multiplying by 1.1, we have got it as 250. And this is divided by the safe bearing capacity, which is 300. Now, can you give me the area? Can you give me area required? Can you tell me how much is your area? Okay. So we have got our area to be 10.5 meters square. Okay, 10.5 meters square. Okay. Now for this particular question, you don't need to write if you don't want. I'm going to post for you the solution. Okay, I'm going to post for you the solution in terms of a picture. You just concentrate. Okay, so we have area required to be 10.5. Now in the previous problems that we have solved, if you remember, if we are having a square footing, square footing is having only one side, which is b into b. Okay, and we used to calculate b by getting the under root of the area. Okay, because there is one unknown, we are able to calculate the dimension. Now when it comes to rectangular, okay, area is equal to length into width. Now to solve these two unknowns, I require 2 equations. One equation is already available, which is area equals to L into B. Another equation is required in order for me to get the 2 dimensions. Otherwise, I'll not be able to get L into B. Okay. So we used to do or whatever we have used to have in the last classes, that we are having another dimension, which is the width, for example. Okay, they have given us that this is restricted to this amount of width, or lateral dimension has been restricted to this much. And I have told you, if it's not given, you need to go and use the ratio of the column. But the problem here, that the columns, both of them are square for me, and my combined foundation cannot be square, or it's not logical to be square. So in this case, if the dimension is not given, if you don't have rectangular column, so what you need to do, you need to use 1:2 ratio, where 1 is going to be your length, or your width, sorry, and 2 times is going to be your length. Okay, so once again, my length is considered as 2 times of my width, which can be written as area equals to L into B, where my L is equal to 2 times of width multiplied by B. So my area is equal to 2B square, and my B is equal to under root of area divided by 2. Can you give me this value? Can you give me this value? Where area is 10.5, this is 12 by 2. So it's approximately 2.3 meter. Okay, approximately 2.3 meter. What about the length? How much is the length? Length is going to be 2 times of 2.3. So that's going to be 4.6 meter. Okay, so what we are going to say? We are going to say adopting or using a foundation which is 2.3 into 4.6. Are we okay till here? Are we fine till now?
Yes.
Everything is fine? Okay. So the next step, which is not available in the isolated foundation, which is going to be center of the foundation. Okay. We are going to check something called center of foundation and center of loading. Now previously, in an isolated foundation, we have only one column, so the center of the loading will be at the center of the column. But if we are having 2 columns, the center of loading will be only at the middle between them if these loadings of the 2 columns are equal. Now, if you remember, we said the larger column would require a larger foundation. The smaller, I mean, in terms of loading, the column which takes lighter loading will have a smaller foundation. So based on this, we are going to work out where is the center of loading, and that center of loading is going to be the same as the center of foundation. Okay. Now what we have, just concentrate here. We have a column which is 300. Let's say here. And then I have a column here. This is 400. We have a loading here, which is 1000, and then 200. If you return back to the question, okay, we have 1200 for column number 1 and 1400, 300 for column number 2. Now let us assume, do you know what you call it? Do you know, can you fix your handwriting? Are you able to see now? I said no need for you to write. I'm going to give you the picture ready. Just 1 second. No, I said for you. I said once again, if one dimension has been given, then use that dimension. If the dimension is not given, use the ratio of the column. If the ratio of the column is square, it does not fit, use 1 to 2. Okay. Now let us assume. Do you know the competition of rope pulling? Do you know the competition of rope pulling? شد الحبل. Do you know? Assume that we are having two persons. One is trying to pull from the left side, one is trying to pull from the right side. If both of them are having the same strength, then you will see that this will stick in the middle. Do you agree? If both of them are having the same strength, they are pulling with the maximum, then you will see that it will, the rope, or if I put them something in the middle of the rope, it will stick in the middle only, right? Now if your left guy is stronger than the right guy, what will happen? Where this will be shifted? Once again, if my left guy is stronger than the right guy, this particular center will be leaning to what? It will come somewhere here, right? It will come to the left side, right? Okay. Now, in my particular scenario, which column is going to be stronger, or which column is taking more load? The right one. So it should lean, the center of gravity, it should lean to the bigger one, right? The center of loading should lean to the right one. Okay, it should lean to the right one because the right one requires more area as well. Okay, so this will be shifted to somewhere here. Now, if both of them are equal, I can say that since this is 3 meter, then this is going to be 1.5 meter, and this is going to be 1.5 meter. That's if it's in the center. Do you agree? Do you agree if it's in the center? Okay. Now, what if it's not in the center? How would you calculate this one? Can you tell me? How would you calculate the distance from the center to the... How would you get this value? Or let's say E value. E value. Okay. Do, do you remember when you have studied in applied mechanics and mechanics of materials something called resultant? Resultant, do you remember? Okay. So what we used to have force number one multiplied by distance number one plus force number two multiplied by distance number two. Okay. Force number one multiplied by distance number two. I mean number one plus force number two multiplied by distance number two is equal to R, which is resultant, multiplied by E. Okay. So in short, we say, we say our moment equals to force into distance is moment. Resultant multiplied by E, or distance. Okay. Now how many forces are available? How many forces are available here? How many forces are available in the system available in front of me now? There are four loading which are available in two columns. Okay, four loadings available in two columns, or if you combine them, two. Okay. Now if I place these two columns or these two loading according to you, or four here, how much are going to be? How much is the total? Can you tell me the total of them? Can you tell me the total force? 1,400 plus 300 plus 1,000 plus 200. This is going to give you how much? 2,900 kilonewtons. Now, if this is going to be my resultant, which is 2,900 as a force, okay, and I have this particular loading, and I have this particular loading, how much is going to be my E? Now, in order to do that, what we need to do, this is a point A, this is a point B. Okay, we have our resultant. In order for us to calculate E, we need to calculate the moment. Okay, now we have loading here, which is 1,200, and then here we have another loading, which is 1,400, and then 300. The distance between these two points, the distance is 3 meters. Okay. Can you calculate for me? M about A? Can you calculate for me moment about A point, or point number A? Moment about A, or point A, will be how much? Okay. Moment about A will be 1,000 plus 200 multiply the distance. What is the distance from this force to point A? It is going to be 0, so this will be cancelled, plus 1,400 plus 300 multiplied by 3, which you have got already. That is equal to 5,100 kilonewton meter. Okay, now we have our M, we have our resultant, and then we have E. Now if I shifted these four forces into one resultant force, okay, at a certain distance of E, it should give me the same moment of the whole system. That's the concept of the resultant. Okay, now if I go and say my MA equals to resultant multiplied by A, sorry, my resultant is 2,900. Okay, alright, let me write it here. So we have 5,100, my resultant is 2,900, and then we have E, let's say EA from A column. Can you give me now EA is equal to how much? Okay, approximately it's 1.76 meter. Approximately it is 1.76 meter. Okay, try to keep it 2 decimals, otherwise you will have a lot of calculation issues, especially in combined foundation. Now we have got our EA equals to how much? We have got our EA equals to 1.76. Now how much is going to be your EB, the distance from column number B, is going to be how much? It is going to be 1.24 meter. Okay, it is going to be 1.24 meter. Are we okay whatever we try to do? Are we fine? We shifted the entire 2 columns loading into 1 point. Why we have put it into 1 point? Because that point is going to be the center of the loading. Now I have only one center. I don't have 2 loadings, only 1 loading with 1 center. Okay. Now if we go and take it, okay, if we go and take it, okay, we have column number A, this is 300, and then we have column number B, that is 400. The distance from the center from the first column to the second column is going to be 3 meters. Okay, the center is going to be 3 meters. Now we said the center, okay, the center should be acting at a distance of 1.76 from here. Okay, so this is going to be my center of loading. Okay, this is going to be my center of loading, and this point is as well going to be the center of my foundation. Now we said it is going to be 4.6 for me, so this distance from this point till the edge of the foundation is going to be as 2.3 meters, which is 4.6 divided by 2, half of the foundation. This distance is my width, which is 2.3 meters. The other half is going to go the same thing, 2.3 meters, okay, which is 4.6 divided by 2. So that's going to be 2.3 meters. Okay, so what I tried to do, I found my center of loading, and I kept that center of loading to be the center of the foundation itself. Okay, I kept that particular point to be the center of the foundation itself. Now we know that the length of the foundation is 4.6, Okay. Let me just do one thing. Okay. Are we clear about whatever I have done till now? Okay. This distance we said from the center to here, we said it's 1.24. Okay. Now can you help me? Can you help me finding this? Can you help me finding this dimension? Let's say B small, and then can you help me in getting this A small? Because for me, before designing or before calculating the bending moment, I should know all the dimensions. How much is your AB? How much is A? And how much is B? Now, if you see A can be calculated as the distance here is 2.3. The distance here is 1.76. So A is equal to 2.3 minus 1.76. Okay, and this is going to be how much for A? For B, the same thing. We're going to be 2.3. Okay, 2.3 minus 1.24, and this is going to give me A is 0.5, 0.454 meter. A is how much? You said 1.06. Now, which one is having higher loads? Column A or column B? Column B. Sorry, column A or column B? Column A or column B? Column B, right? Logically, based on the loading, which one's supposed to be having a higher distance to the edge? Means higher area. Is it column number A footing or column number B footing if they are isolated? Now you can see for column number A, the distance from the center to the edge of the foundation is 0.54 because the loading is less. For column number B, if it's an isolated foundation, you will see that the distance is more. It is 1.06 because the loading is more than case number A. Are we clear? Okay. So once again, this confirms whatever we have studied earlier. Okay. So this is regarding. Okay. So this is regarding calculation of the dimensions. Now the next step is to go for the bending moment diagrams. Okay, for the bending moment diagram. So let me just have it here. Let's just go now. Okay. Now before we go and calculate the bending moment, we need to go and calculate our pressure. Okay, we need to calculate our pressure. Let me just have it like this. Can you tell me how much or how to calculate your pressure? If you remember, pressure is calculated, or let's say ultimate pressure. How to calculate ultimate pressure? Ultimate pressure is going to be ultimate load divided by your area. What is your ultimate load? Returning back to the question, we have two dead loads, we have two live loads. Okay, dead loads are 1000 and 1400. So what I'm going to do, I'm going to multiply 1.4 into 1000 and 1400 plus 1.6 into live loads. How much are the live loads to this? We have 300 and we have 200. So I took them, 200 plus 300 divided by my area. What is my area? My area is 2.3 multiplied by 4.6 meters. Can you give me how much is this value? How much is this value? Can you just confirm? Yeah, I think it's 393. It says 393 point something. Okay. Okay. So 393.19 or 0.2 approximately. Now in isolated foundation we used to multiply by 1 meter width. Okay, in isolated foundation. In slabs we used to multiply by 1 meter width. Now when it comes to combined foundation, we multiply by the full width. Okay, my full width is 2.3, which is 2.3 here. Now I want you to think, till the next class, okay, why, or search about it, why in the isolated foundation we multiply by 1 meter, and why in a combined foundation we multiply by 2.3. Why we design the isolated foundation or a slab for a strip of 1 meter, and why we design the combined foundation for a strip of a full width. Okay, so think of it and then we'll discuss it next class. Now if you multiply it by the full width, how much is going to be your pressure? And whoever gets the answer correct, he will get 1 mark in his mid exam. So 904, let us say 904 kilonewton per meter. Okay, so 904. Yeah, because this 393.2 was rounded from the beginning, so approximately it's 904. Okay, approximately it's 904. Now we are going to the next step. We are going to check how much is going to be our depth, because we are going to require it. Okay. So calculation effective depth. And we said normally we assume the depth of the coefficient, and based on the depth of the foundation, we will be calculating the effective depth. Okay, so since it's a combined foundation, and the loading is more than 1000, so normally the depth goes a little bit higher. So here I'm going to assume my depth equals to 800 mm. Okay, I'm going to assume that my depth is going to equal to 800 mm, and we are going to see, okay, whether 800 is going to be sufficient or we need to increase extra depth. Okay, so once again we said for the depth of the foundation it's a trial and error. We try a depth. If it does not work, in shear especially, we increase the depth. Okay, so if my depth is 800, and just I write here assumed for your reference when you study. Now if I want to calculate dx, then dx is calculated as d minus cover minus diameter over 2. My depth is 800. Okay, my depth is 800. My cover is how much? My cover is 50 mm. Diameter. So once again here for the diameter I'm going to assume 20 mm. Once again the loading is a bit high. So 20 divided by 2. Or let us, rather than using it always as 20, let us use it as 16. Let us change a little bit. We will use it as 16. Okay, it will come out 742 millimeters. This is my dx. What about dy? dy is equal to dx minus diameter. So that's 742 minus 16. How much is this? 726 millimeters. Okay. Now we don't use dx or dy. We normally use d average. So my d average is dx plus dy divided by 2. So how much is my d average? My d average is how much? 734. So this is going to be the value to be used. Okay, this is going to be the value to be used. Now we have calculated our pressure. We have calculated, or we have got our depth. Okay. Now the remaining thing is to calculate for the bending moment. And for the bending moment, please concentrate with me because it requires a lot of concentration. Last time in the last class we have done one small mistake and then we have got different values. Okay, so just be careful when you calculate with me. Okay, so once again what we are going to try to do, let me write this here, number 5 now. I hope number 5 is the correct number. So bending moment and shear force. Diagrams. Okay. Now what we are going to do, I'm going to draw a plain reference line. I'm going to show all the dimensions. Okay. So what we have one point here. We have another point here. The distance between these 2 points. Okay. The distance is 3 meters. We have one column here. We have another column here. Okay. And then this is a column of 150, this is a column of 300, and this is 400. So we have here, I'll just have it as 0.15, and this one as 0.15, here as 0.2, and this one as 0.2. Okay. Now, what I want you to do, I want you to tell me how much is this distance, the distance from here to here, from here to here, how much is it? From here to here, how much is it? And then the distance from here to here. Remember in the previous A and B, the small letters, we calculated from the center of the column. We said that this one is how much? We said this one is how much, and this one is how much? Okay. If you remember, we said, I will go and see it from here. We said that's one, no, and here we said 0.54 and 1.06. So we have this distance as 0.54. We have this distance as 1.06. Now, if the distance from the center of the column till the foundation is these two values, how much are from the face of the column till the edge of the foundation? At the left, it is going to be 0.39. How did we calculate 0.39? It is going to be 0.54 minus 0.15. So this is 0.39. Be careful. Whenever your diagram is clear, the calculation of the dimensions wouldn't be hard. If you missed any of the values, then the whole diagram will be wrong. You cannot get the correct value of bending moment. The other direction is 0.86. Okay, the other direction is 0.86. Now, if we calculate 0.86, if we open our calculator, and to confirm, we're going to go 0.39, the distance from the left edge of the foundation till the face of the column, plus we have the column which is 300, plus we have 3 meter between, not 3 meter, now it is going to be, how much is this? From here to here, from the face to the face, how much is it going to be? It is going to be 2.65. 3 minus 0.15 minus 0.2. The center to center distance is 3 meters. If we are taking from the face, it is going to be 2.65. So 0.39, the distance from the face of the footing till the face of the column, plus we have 300. Okay, so plus 0.3. Plus the distance from the face of the column to the other face of the column, this is going to be 2.65. That is 3 meter minus half of the first column, which is 0.2, minus half of the second column, which is 0.15. Okay, plus the second column, which is 0.4, 0.86, which is the remaining distance. So now we have confirmed that these values are correct values. Okay, we have confirmed that these values are the correct values. Okay. Now, what do we have? We have a pressure here. Okay, we have a pressure. We have a pressure which is 904 kilonewton meter. And we have two loads here. What is the ultimate load for column number A and what is the ultimate load for column number B? Can you calculate for me the ultimate loads for column number 1 and column number 2? Column number A is taking 1,200 as alive, 1,000 as dead. Column number 2 is taking 1,400 and 300. Can you tell me column number 1 is going to be having an ultimate load of how much? Yes? Okay. So column number 1 is going to be 1.4 into 1,000 plus 1.6 into 200, and this is going to give you as 1,720, right? Okay, as 1,720. What about the second one? What about the second one? The second one is 1.4 multiplied by 1,400 plus 1.6 multiplied by 300. This is going to be how much? $2,440 kilonewtons. So now we have our loadings, we have our dimensions. It's a matter of calculation of bending moments and shear forces. Okay. Let me just try to have different points. Okay, I'll have different points and then we'll see. Now let us see point number 0, and then we have point number 1 and point number 2. We have point number, let's say 3. We have point number 4, and then we have point number 5 for the meantime. Okay, so we have 5 points. Okay, we have 5 points. Now for point number 0, how much is your shear force? Can you tell me? Point number 0, how much is your shear force and how much is your moment for point number 0? Okay, it is going to be 0. From the definition of shear force, it is for you the total or the sum of the forces on the right side or the left side. Now, do you have on the left of point 0, do you have any forces on the left side? Do you have any forces on the left side of 0, point 0? No. So if there are no forces, then directly you can say that shear force is 0. Now, if there are no forces, once again you can say that the bending moment is equal to 0. So now we know that this point is 0 and this point is 0. What about V5 and M5? V5 and then M5. How much is shear force at point number 5 and how much is moment at point number 5? Once again at 0. From the definition, on the right or the left, I'll see the easiest one. The easiest one is to go to the right. There are no forces on the right of point number 5, so my shear force is equal to 0. And then my moment, of course, if no force, then my moment is equal to 0. Are we okay with these points? Are we okay till now? Okay, very good. Very good. Now we are going to calculate for point number 1. Okay, we are going to calculate for point number 1. Now, if you see, for point number 1, it acts like this. So this is my point number one, where it acts like a fixed. And then this is going to be the remaining portion. The distance from the point that we want to calculate till, or let me draw it at the top. The distance from the point that we need to calculate till the edge is 0.3 meters. And we have one loading which is available, which is a pressure. Now this pressure is 904 kN per meter. Now this acts like a cantilever. This acts like as a cantilever with a point load. Can you tell me how much is the bending moment for a cantilever? Bending moment for a cantilever is equals to W square over 2 if it's a UDL. Okay. And shear force is equal to W into L, force into distance. If you have force into distance, it will give you the moment. Now, if we multiply 904 into 0.39, can you give me the shear force first? Can you give me the shear force first? How much is your shear force if we multiply 904 multiplied by 0.39? 904 multiplied by 0.39. This will give you 352.56. Okay. So what I know that this will go up. Okay. This will go up by the value of 352.56. Now the bending moment can be calculated in two ways. Okay, in two ways. You can use the equation, which is W square over 2, in which we are going to get 904 multiplied by 0.39 square divided by 2. Okay, and you will have the value of the moment. Or you should have studied that you can calculate the bending moment value using the area of the shear force. Now my area of the shear force is actually a triangle for the same position. The height is 352.56. The base is 0.39. If you got the area of the triangle, then it's half into base into height. Can you give me the bending moment values? This is using the equation 68.57.75. What about using the triangle? Using the triangle, 68.75. Okay. So you have two methods. Okay, you have two methods. You can choose whatever method you want. Okay, there are two methods. You can choose whatever you feel better for you. Okay, so now I'm going to plot my, of course it's a UDL, so it goes parabolic, and this is my point of 68.75. Any question till now? Do you have any question till now? Very good. Now let us calculate point number 4. Okay, let us calculate point number 4. What about point number 4 now? If you see for point number 4, once again, this is my 4 till the edge of the foundation. The distance here is 0.86. What are the loadings available on this particular location from 4 till the edge of the foundation? Do we have only upward force or downward force? Do we have only pressure or we have the loading of the column? or both of them? From point number 4 to point number 5. From point number 4 till the edge of the foundation, there is only the pressure. Okay, there is only the pressure. The column loading is not contributing in the points or region from 4 to 5. Okay, and once again, this is going to be as 904. We said directly, now we will be a little bit faster. We said my shear force is equal to WL. This is going to be 904 multiplied by 0.86. My moment is equal to WL square over 2, which is 904 multiplied by 0.86 square divided by 2. Okay, so it's like a direct substitution of the values. Can you give me your shear force? Start with the shear force. Shear force. My shear force is 904 multiplied by 0.86. So this is 777.44 kilonewton. The bending moment is 904 multiplied by 0.86 multiplied by 0.86 divided by 2. 334.683 kilonewton meter. Are we okay till now? Are we fine? So once again, if your drawing is clear, your dimensions are clear for you, you understood the concept, you shouldn't have any issue. Okay. Now we have 777.44 and then we have 334.3. So I'm going to plot first the moment. So this is going to be 300 somewhere here. This is not to the scale once again. Okay. So 334.3. Okay, and then we have shear force. Now, one thing you need to take into account when you are going to do the shear force. Okay, one thing to be taken into account. If you started from the other side, then you should flip. You should flip your direction of drawing. Okay, and you will see later when we are going to summarize it. So now, by flipping it, we have 777.44. So it will come like this. It is going to be opposite of whatever you started in the on the left side. Okay, and we are going to summarize it and see later why it came like this. Okay, so 777.44. Now what about point number 2 and point number 3? Can we take point number 2 now? Okay, can we take point number 2? So once again, we'll just draw a line. Okay, we'll say point number 2 here. I'm going to draw a line. Okay. Now if you see, for point number 2, this is my point number 2. Okay. Now what do we have? We have 0.39. Okay, we have 0.39 here. Plus we have, how much is this? How much is the column side? How much is the column side? The column side? 0.3. So if we check them, 0.39 plus 0.3 is going to give you 0.69. So my length, okay, my length from point number 2 till the edge of the foundation is going to be 0.69. Okay. What do we have? We have a pressure. we will see that we have a pressure here all over the place. Okay, we have a pressure all over the place. Do we have column in region of 0 to 2? We always take it from the point of moment, or the point where we want to calculate the moment, till the edge. Now, if the edge is 0, from 2 to 0, do we have a point load? Do we have a point load? Yes. Okay, how much is it? 1720. The distance from section number 2, or point number 2, and the column is 0.15. Okay, so I'm going to come here. I'm going to do 1 point load here. It has a value of 1720, and then the distance from here to here is 0.15. Now we are going to calculate the moment. Or let us start with the shear force. Shear force for a UDL, the shear force is equal to W multiplied by L. Okay, force into distance. That's for a UDL. What about point load? You will see. Now this is taking a positive sign because it goes upward. The column is going downward, so it goes as minus. Okay. How it's going to be calculated is going to be calculated as P only, which is a point load. Okay. So we have WL, which is for a UDL, minus P for a point load. W is how much? W is 904. My distance is 0.69 minus 1720. Can you give me this value? It goes as minus 1096.24 kilometers. Okay, no problem. Let us go for the moment. The moment for a UDL, we said it's WL square over 2. For a UDL, it's WL square over 2. For a point load, once again, it goes minus because it's opposite to the first direction. Okay, how to calculate the moment for point load? It is calculated as force into distance, so P into L. So WL square, we have 904 multiplied by 0.69, which is the distance of the UDL, or the pressure, divided by 2, minus 1720, okay, multiplied by 0.15. Can you give me this value? It goes as minus 42.8 kilonewtons. Very good. Very good. Now, okay. So now, if you see, for point number 2, or for point number 1, my moment value was positive. Can you see in point number 1, when we have calculated the moment, we have done it positive, and it was downward. Now the new calculated moment for point number 2, it is negative, so it goes above the reference line. Previously, the positive goes down. Okay, the positive goes down as whatever we have drawn, and if we are getting it negative, it goes the other side. Okay, so now what do we have? We're going to have it like this, somewhere like this. Okay, this is going to be 42.8. Okay, 42.8. What about shear force? Now you will see, for the shear force, this part of the pressure will take me up. The loading of the column will take me down, right? The loading of the column will take me down. Now you see, when we have taken the shear force, 352.56 is positive, and I have drawn my positive upwards. Okay, my shear force for point number 1 is positive, so I have drawn it in the as my sign convention. I have drawn it. I have drawn the positive for shear force up. Okay, and I have drawn for my bending moment. I have drawn the positive goes down. Now, if you see, for point number 1, we have got the shear force to be positive, so it goes above the line, above the reference line, which is in blue. What about the point number 2? In point number 2, you will see that my loading is negative. It means that it goes below the reference line. Okay, it goes below the reference line. Okay, it goes below the reference line. Now, before doing anything here, now actually in reality, this column is only available at the center. This loading, is it only available at the center of the column? Is it actually in nature, the loading which is available in the column only will act on a certain point of the column, or it will act on all the line of the column, or all the parameter, let's say, or all the size of the column? In reality, the loading which is coming on the column, is it only acting at the center of the column, or the loading will go all over the column? Is it a point load in nature, or is it everywhere? The loading is taken everywhere on the column itself. Okay, so you will see that in reality, it does not act as a point load. In reality, it does act as a UDL. My loading is distributed all over the column. It's not available in one single point. So an accurate representation of the load is not a point load. The accurate representation is a UDL. Okay, the accurate representation is a UDL. So now you can see here, we have positive, we said, for shear force going up, negative goes down, and we have a value of, we have a negative value of 1096.24. Now what you can notice here, because of the, in this region, because of the pressure which is going up, my shear force went up. Here, because of the loading of the column which is going down, my loading went down. Can you see that you went up here and then you went down here? Okay. Now this is for point number 2. Can we go for point number 4? Because we are already late. Point number 4. Or point number 3, sorry. Point number 3. So this is my point number 3. I'm going to be a little bit fast. Okay. So we have how much here? We have this one, 0.86. And this one, 0.4. 0.86 plus 0.4. This is going to be as 1.26, right? So we have the distance from here as 1.26 meter. Okay, 1.26 meter. There is a pressure, and then we have a point load. The distance from my point number 3 to the point load has been given as 0.2. So I'm going to draw this here, 2440, and then the distance from here to here is 0.2. So now to calculate my shear force, once again, it is going to be WL minus P for the point load. We have UDL and point load. UDL is 904 multiplied by the distance of the UDL, which is 1.26. Point load is 2440. Can you give me the value? For the moment, for the UDL, my moment is WL square over 2. For my point load, it is force into distance, so P into L. We have this one as 1,300.96 kilonewton. What about the moment? What about the moment? The moment is the moment is 904 multiplied by the distance, which is 1.26 squared, divided by 2 minus 2,440 multiplied by 0.2. How much is your moment? How much is your moment? Can you just cross-check? I think your answers are wrong. It is 229.6. Once again, be careful. One value is wrong in the bending moment diagram, it will crush all of your answer. Okay, so it's 229.6, 229.6 kilonewton meter. Okay, so now you see. Once again, here it was 334. Now it's reduced to 229. So it goes like this. Okay. Once again, this is not to the scale. Let me just redraw. Somehow. 229 point how much? 0.6. Just redraw this one so it will make some sense. Okay. Now for the shear force, we have got it to be how much? We have got it as 1,300.96. Once again, we are going from the right side, so we flip everything. Okay, we flip everything. So this goes up. By the value of 1,300.96. And if you see, to conclude, this is going to be connected now. Okay, to make it a bit easy for you, this region, we have pressure only, so pressure will put me up. So I went up here. This point where the column is acting, the column is going downwards, so it goes down. This point here, we have pressure, so it will take you up. This region, we have a column will take you down, so we went down. This portion, it goes pressure only, which will take you up. Okay, so it's a matter of up and down. Okay, it's a matter of up and down. The position where we have pressure, it goes up. Wherever we have column, it goes down. Pressure, it goes up. Column, it goes down. Pressure, it goes up. Okay. This is very accurate. Let us keep it here. Are we okay? Are we fine with whatever I have done? Okay. Now the last thing for me is to calculate the maximum bending moment. And the maximum bending moment occurs where the bending moment maximum occurs. Maximum bending moment occurs wherever bending moment goes, or wherever shear force goes 0, right? at zero shear force, and this is the point of zero shear force. This is the point of zero shear force. We need to calculate the moment here. Now, in order for you to calculate the moment, can you tell me how much is this distance? Can you tell me how much is this distance? Let us call it as x. How much is this distance? Okay. Now x can be calculated. X can be calculated. X is a distance, so it's in meter. Okay. You have your force divided by your pressure. Force, which is in kilonewton. Pressure is in kilonewton per meter. Kilonewton will go kilonewton. Meter will go up. Okay. So I need to know if I have a pressure of in this location, if I have a pressure of 904 and my point is 1096.24 here, how much distance of 904 which will make it 0? Okay, how much will make it 0? Okay, it is like saying 1960 point how much, 0.24 equals to 904 multiplied by the distance of x. Okay, remember that 1096 is down and then 904 is going up, so they will counteract each other. Okay, so how much is this? This is, as we said, it is going to be the force, which is 1096.24 divided by the pressure, which is 904. How much is this value? How much is this value? It goes as 1.21 meter. Okay, let us say 1.21 meter. Okay, 1.21 meter. Now, what we need to do, in order for us to draw or to get the bending moment, what we need to do, we need to take this particular portion, okay, all of this particular portion, all of it. Okay, so what do we have? I'm going to draw a line first. Okay, so this is my line. What is the distance of the line? Okay, what is the distance? We have 0.54 from here. We have another 0.15 from here. And then we have this distance has been calculated as 1.21, which is x value. So 0.54 is till the center of the column, and then 0.15 from the center till the edge, and then we have 1.21, which is calculated as your x value. Can you give me how much is this value? Can you give me how much is this value? How much is this value? Any person? It is going to be 1.9. Okay. So this is going to be the distance that we have a pressure here. Okay. The distance is 1.9 meter. So I have just drawn 1.9 meter. In this particular region, this is 904 kilonewton meter. In this region, do we have a column? In this brown box that I have drawn, do we have a column? Do we have a column? Okay. What is the distance between the column till the new point? Let's call it point number 6. From point number 6 to the column is how much? if you see, it is going to be 1.21 plus 0.15, right? From the center of the column till point number 6, it is 1.21 plus 0.15. So it is going to be 1.36. So we have a loading here. Let us plot here. Okay. The distance is 1.36. This is 1,720. So 1.36 meters. Now can we check by calculating how much is my shear? If you remember, your shear is WL for UDL minus P. So that is going to be 904 multiplied by the distance of UDL, which is 1.9 minus 904. Your value should be very close to 0, if not accurately 0. If you are taking all the decimals, not only 2 decimals, you should be getting exact value of 0. How much is your shear force? How much is your shear force? It's not possible. Sorry, this is 104. My bad. This is 1,720. The point load is 1,720. Okay. Approximately 0 if you take. Okay, so some of you have got it to be minus 2.4. Once again, if you take more decimals, okay, if you take more decimals, you will get it as 0. Okay, so 2.4 is almost 0. Now, what about the bending moment? Bending moment is WL squared over 2 for the UDL, okay, minus P over L, or P multiplied by L for the point load. So we have 904 multiplied by 1.9 square divided by 2 minus 1,720 multiplied by the distance, which is 1.36. Force into distance. Can you give me how much is this value? Your value is minus 707.48 kilonewton. And once again, this is negative, so it goes up. So it confirms my solution that this point is actually up, which is 707.48. Now, if you see, do you have moments at the top of the reference line? Do you have negative and positive moments? Do you have moments at the top and the bottom? Do you have moments at the top and the bottom? Okay. So what you need to do now, you will be having 2 moments. Okay, you will be having 2 moments. One is the higher value, and the other one. Okay. So we have two values. One which is representing the column side, one which is representing the span side. Okay, one which is representing the column, one which is representing the side. Okay. So this is a column moment, which represent top reinforcement. This is span moment, which represent bottom reinforcement. So now you have 2 values of, this is in the longer direction. Okay, in the longer direction, you will be having bottom reinforcement, top reinforcement. How would you calculate them? You have 2 moments already. One at the face of the column, one is the span moment. You need to calculate K, Z, AS, and whatever to get your values of reinforcement. Okay, which are typical steps that I'll not go through. Now, if you see, one thing before finishing. Okay, if you see, just 1 second, for those who are having classes, they may leave after I take the attendance. Just 1 second. Okay, only if you have a class, because whatever I'm going to explain is important. Okay, now if you see, we said for a combined foundation, we have two dimensions. One is 4.6, another one is 2.3. Now if you see, we have one column here, we have another column here. My bending moment, my typical bending moment in this direction is going to be somewhere like this. Okay, or it goes like this. This is for the longer direction. For my shorter direction, you can see in the longer direction, I'll face two columns. So it acts as a combined foundation. In the shorter direction, it acts as a isolated only. If you see, you will see one column. Okay. So you will be having what you are going to have here. You will have one distance here, and you will have one distance here, L1 and L2. You will be taking the higher of the two to calculate the moment on the other side. If you remember what we said, we are going to say that we have top reinforcement here, or bottom reinforcement. We have top reinforcement here. This column side, okay, this column side is representing your top reinforcement. This span moment is going to be representing your bottom reinforcement. This is in one direction. In the other direction, okay, in the other direction, you need to take into account this particular moment, and once again, you need to calculate it at the face of the column. Okay. The most important thing for me when it comes to your examination, the most important thing for me is that you should know how to calculate the bending moment on the longer direction. Okay. On the shorter direction, you already took the isolated, so you shouldn't have any problem with it. Doing that, we have finished today's session. I'm going to send for you later the solution. If you have any question, you can ask. If you don't have any question, then you are free to leave.